Good morning, good afternoon, good evening, whatever the case may be. We are back and better than ever, and today we are talking about zeros, roots, and factors of polynomials as we begin the lesson with Angels and Airwaves, the adventure. The adventure begins, so let's get to it, shall we? All right, so zeros, roots, and factors. What are the difference, particularly with zeros and roots? A zero of a polynomial is a value of the variable which makes the polynomial equal to zero. Alpha is a zero of the polynomial p of x if and only if p of alpha equals zero. This will become clearer in just a second. The upshot is a zero of a polynomial is just the polynomial. It's not an equation. It's what you substitute in to the polynomial to make it zero. The roots are the solutions of the equation. So you can use roots and solutions almost interchangeably. Okay, and altogether now the roots are the roots of the equation when you set the polynomial equal to zero are the zeros of the polynomial that's not an equation and the x-intercepts of the graph of the polynomial. Got all that? All right. So if x minus alpha is a factor of a polynomial p of x, there exists a polynomial q of x such that p of x equals x minus alpha times q of x. All right, that's a whole lot of mathematical speak. So if we were just asked to find the zeros of a polynomial, such as x squared minus 4x plus 53, we're really solving the equation. Okay, we're setting it equal to zero. So we could use the quadratic formula, and I'm not going to bore you showing you that. I'm just going to say it simplifies to 4 plus or minus 14i over 2, and then we can simplify that to 2 plus or minus 7i plus or minus 7i, dividing both sides by 2. So these two values would be the zeros. Same idea here. This factors into, we'd have to set it equal to 0, which seems kind of silly. Z times z squared plus 3 equals 0. So then we would have z plus I root 3, z minus I root 3. We've done this before, equal to 0. So then the zeros would be negative I root 3, 0, and I root 3. Okay? Just giving you the distinction. Now, we're going to find all the cubic polynomials that have zeros of 1/2 and negative 3 plus or minus 2i. And even though we're finding all cubic polynomials, we can still use this formula that we have to find the equation given complex roots. So let's do that real quick. It's a nice little quick way to do this. Of course, we could always say that the polynomial could be a times x minus 1/2 times x. If I subtract, so that would be plus 3 minus 2i. Sorry, I ran out of room, times x plus 3 plus 2i. And we could multiply these out and simplify. But if we can just consider the roots, negative 3 plus or minus 2i, so this is our c and this is our d, then I know that the quadratic roots would be x squared minus 2 times c, or 2 times negative 3. So a negative is going to be plus 6x, and that just comes from right here, plus c squared plus d squared. So that's going to be 9 plus 4 plus 13. Okay, so I get x squared plus 6x plus 13 just from these two roots. And if a 0 is 1/2, I also know that x minus 1/2 has to be a factor. And so I have my cubic. I have one cubic, actually, a cubic polynomial, because x times x is x cubed. But if I want to say all cubic polynomials with these zeros, I would have to put a in there, where a is a constant and a is not equal to 0. And I suppose to make it official, the polynomial would be a times x minus 1/2 times x squared plus 6x plus 13. And then a could not be equal to 0, obviously. Could be anything else. Now, this is a very nice thing to have in your back pocket, not on your formula booklet, but if you can remember this, it's going to, it's going to save you some time. All right, so now let's consider something a little bit different, because we don't have imaginary roots here. We have 1, 2, 3, 4 roots, okay? But if we think, well, first of all, with 2 and minus 3, we know that we're going to have a times x minus 2 times x plus 1/3 for sure. We know that, okay? And we could multiply all that out, but it would be messy, and they're not asking us to. They're just asking us to find all quartics. Now, if I have -1 plus root 5 and -1 minus root 5, those are two roots of a quadratic. So with that, I can do my alpha plus beta is equal to -b over a. And if we add these two, we end up with -2. So that means that b over a is equal to 2. And then alpha times beta, -1 plus 5 times -1 minus 5, that turns out to be -4, which is equal to c over a. Okay, so clearly we can see that a is equal to 1, and if a is equal to 1, b is equal to 2, and then c is equal to -4. So from these roots, I get the quadratic x squared plus 2x minus 4. Okay, and here's my other two roots, which are x minus 2. I guess I'm putting them in different order, whatever. X plus 1/3. Put the a out in front, and I have the quartic, or all quartic polynomials with these zeros. Okay, so nice little tools to have there. Okay, let's do some more examples. Find constants a and b if z to the 4th plus 9 equals all of this nonsense for all z. Okay, well, we have this, so we're going to have to clean this up just a little bit. Z to the 4th plus 9 is equal to, and if I multiply this out, I get z to the 4th plus bz cubed plus 3z squared. Multiply through by the az, I get az cubed. And I'm lining up my like variables and exponents, plus abz squared plus 3az. And finally, multiplying through by 3, I get 3z squared plus 3bz plus 9. Okay, and if we clean all of that up, I get z to the 4th plus 9 is equal to z to the 4th plus a plus bz cubed. Oops, why did I do that? It's not an exponent. A plus bz cubed plus ab plus 6. Oops, not ab, not a plus b, ab. Z cubed, sorry, plus AB plus 6 z squared plus 3a plus bz, or 3b I should say, plus 9. Okay, so that all stems from this. And if we start equating coefficients, well, a plus b must equal 0 from here because there's no z cubed. AB plus 6 must also equal 0 because there's no squared. And 3a plus 3b must also equal 0. So from equation, let's go ahead and say equation 1, 2, and 3. From equation 1 and 3, we can see that b is equal to negative a. So using substitution here with b equal to negative a, I get a times negative a plus 6 equals 0. A squared equals 6, so a is equal to plus or minus root 6. So that means b, if b is equal to negative a is equal to negative b, we just reverse the signs, minus plus root 6. In other words, when a is positive root 6, b must be negative root 6, and vice versa. So those are our solutions. A could equal root 6, while b is equal to negative root 6, or a could equal negative root 6, while b is equal to positive root 6. So those would be the constants a and b. We have answered that question. All right, so that puts us at a good stopping point. This will be part 1. We'll do a part 2 up. And with that, I am able to say that I am out.